So the way to make this problem more tractable is to turn it into a linear algebra problem. The great things about linear algebra are, 1, it's easy to scale to higher dimensions. You just increase the size of your matrix, nothing is harder. More calculations, but same principle. And then the second thing is it's very easy for a computer to do. We're not going to be programming them, but you could if you wanted to, and you could solve higher dimensional linear programming problems pretty quickly. So let's look at this problem, which is given to us already in variable format, so we don't have to worry about translating from words. We're maximizing 2x1 minus 3x2, and we've got some conditions. 2x1 plus x2 is less than or equal to 12, x1 minus 3x2 is less than or equal to 5, x1 and x2 are both non-negative. So first thing we're going to do is we're going to add slack variables. 2x1 plus x2, we need some non-negative number x3 to add all the way up to 12 if we're not there yet. And then x1 minus 3x2, we need some other non-negative number, let's call it x4, to add all the way up to 5 if we're not there yet. And now x1, x2, x3, and x4 are all non-negative. The thing we're maximizing we'll call z. Z equals 2x1 minus 3x2, or in other words, z minus 2x1 plus 3x2 is equal to 0. Now we've got these three equations. We're going to put it basically in a matrix format. We'll have z on the left, x1, x2, x3, and x4, and then a value on the right-hand side. Okay, so first equation is 1z minus 2x1 plus 3x2 plus 0x3 plus 0x4 equals 0. This equation, we have 0 z's, 2x1, 1x2, 1x3, no x4s, that equals 12. And then this equation, we have 0 z's, 1x1, negative 3 x2s, 0 x3s, 1 x4 equals 5. Okay, now we notice, recall row-reduced echelon form. Basically, this is not in row-reduced echelon form, but the basic premise of that form is to make the identity matrix somewhere, and you can have junk columns, and maybe, basically junk columns afterwards if there are too many columns. Well, look, these two are junk columns. If we just erase those, we have an identity matrix here. And we can read off a solution. So if we call these junk columns, meaning we're going to set x1 equal to x2 equal to 0, that means we can disregard these columns. This is going to be one corner of our feasible region, corresponding to x1 equals x2 equals 0. In fact, it'll be the origin if we just draw the two-dimensional version. Then we get x3 is 12, x4 is 5, and z is 0. So if we're trying to maximize z, 0 is probably not the maximum. Okay, that's one corner. How do we get to other corners from here? How do we get to, in fact, we don't care about every corner, we just want to get to a better corner. Do we know that there's a better corner? We do from this. If you have a negative coefficient over here, what does that mean? That means you can add, remember our row operations, which will keep all our equations true. You can add another row or a multiple of another row to the first row. And since these guys are all non-negative, that will increase your value of z. So we can add another row. We're going to cancel this out. So we're going to make this column now part of the identity matrix. We'll make a 1 somewhere here, 0s everywhere else. And we're going to switch to a different corner where x1 is not 0. Okay, which one should we add? Let's look. If we scaled this number to 1, then over here we would have a 6. So let's just write that down. 12 over 2 equals 6. If we scaled this number to 1, it's already scaled. But let's just scale it for fun. Anyways, 5 over 1 equals 5. If we scaled this one to 1 and canceled this one out, then that subtraction basically would make this number negative. We don't want that. We want to keep everything over here positive. So we will scale this number to 1. So basically we're taking ratios of the right-hand side over the coefficients in the column we want to scale, and the smallest positive number that shows up will be our candidate. Okay, so we go in this row, make sure the x1 coefficient here is 1, which it already is, and then we're going to add multiples of this to the other rows. So we'll add double the third row to the second row, subtract double the third row from the second row and add double the third row to the first row. And we get a new matrix. We get 1, 0, negative 3, 0, 2, 10. 2 times 5 is 10. And then 0, 0, 7, 1, negative 2, 2, 0, 1, negative 3, 0, 1, 5. Okay, let's look at what happened. Now we've got these two junk columns, which if we get rid of those, we have an identity matrix left. It's not in the right order. It will go Z, x3, then x1. But basically an identity matrix. And then we have this new corner, which is going to be better, corresponding to x2 equals x4 equals 0. And then if those are 0, then x1 must be 5, x3 must be 2, and then z is going to be 10. 10 is bigger than 0, so we've improved our maximum. Can we improve it any more? Yes, we can, because we still have a negative entry in that first row. Okay, what can we do now? Let's look at these ratios. We've got 2 over 7 for this row, and we've got 5 over negative 3, negative 5/3. Okay, so if we do this, we're going to be subtracting here. We'll actually make the z value smaller. So that's bad. So we want the smallest positive number. In this case, it's the only positive number. So we're going to scale based, sorry, can't see this. Smallest positive number. This one's negative. We're going to scale based on this row. So we'll first divide through by 7, so we have a 1 here. And then we'll add multiples to the other rows. I'll let you do that on your own. You can see if you get the same answer as me. Again, 1, 0, 0, 3/7. Got some uglier numbers here. 76 over 7. 0, 0, 1, 1/7, negative 2/7, 2/7, 0, 1, 0, 3/7, 1/7, 41/7. And behold, we've got two junk columns. Cross those out. This is some permutation of the columns of an identity matrix. We look at our values. So here we have x3 equals x4 equals 0. So in fact, if we had done this problem vanilla style and graphed it, this would have corresponded to the point of intersection of the two interesting lines, because our x1 and x2 will have non-zero values. But let's just see what they are. x1 is 41 over 7, x2 is 2/7, and our z value is 76 over 7. So remember, before z was 10, 70 over 7 would be 10, so this is in fact bigger. Now we look at the first row. There's no negative coefficients there, so this is our final optimal value of z, and we know what values of x1 and x2 give us that. That is the simplex method.